All right, we're going to pick up where we left off with day number 2 of finding limits analytically. And we're going to get some trigonometry into the picture here. There's a very important formula that's really understated in a lot of books. It's the fact that sine of x over x equals 1 if you're anywhere near 0. Okay, the limit as x approaches 0 of sine of x over x equals 1. Now, in calculus, you have to be in radians 100% of the time. It's not like pre-calc where it's a 50-50 deal between degrees and radians. You're mixing trig and non-trig, so you must be in radian mode. And again, it's because radians are dimensionless. So we're going to use this little tidbit of information to work on some problems starting up right now with number 11.
So the answer to number 11 is simply 3. And the reason why is we're near 0, so this sine of x over x turns into a giant 1, and you have 3 times 1, which is 3. Now here at number 12, we have to be careful because unlike number 11, where these were matching each other, they are not matching. And so you need to make them match. So what you can do is multiply top and bottom, numerator and denominator, by the same thing. That way you can claim it's a giant 1. And the thing is going to be a 6/7. So 6/7 over 6/7, that's just a big blue 1. The reason I'm doing this is so in the denominator, the 7s will cancel. So what that is going to yield is 6/7 sine of 6x in the numerator. The denominator will simply be 6x. And now these are the same. And so since we're heading towards 0, this will be a giant 1. And 6/7 times 1 is 6/7. And then, of course, I get students who are like, can't we just look right here? We know the answer is 6/7. And I'm like, yeah, you can. That'll work like 100% of the time. But I wanted to show you the legit steps behind the scenes so that you didn't just think it was magic. So yeah, use the shortcut. That's fine. We're back to the greatest integer function, int of x. That's the same thing as having the x inside the greatest integer bars. Okay. So really, we're approaching 6 from the right. So we're plugging in numbers like 6.01 to the greatest integer function. What's that going to be equal to? And the answer is 6. It's like you just had your birthday and you turned 6 and you're 6 at your age. But what if you're approaching 6 from the left? Meaning that you're plugging in numbers like 5.99. Guess how old you still are? Yeah, you're not 6, you're 5. It rounds you all the way back to the last birthday, the greatest birthday that you had, the greatest integer. Okay, so it's not a round off, it's a round down. All right, let's plug a -2 into the greatest integer function, but we're heading towards -2 from the left. So that's really like -2.01. We saw this a little bit on the review day. It's not going to be -2, it's -3. -2 has not occurred yet. We're not far enough to the right on the number line to hit that. We have to round back down to -3. All right, so far so good with greatest integer functions. Number 16 is the limit as x approaches 0 from the left. So we're plugging in numbers that are very close to 0, but they're negative. It's like -0.01, we'll say. If you plugged in a -0.01 to the numerator, it would get absolute valued. If you plug the -0.01 into the denominator, it would not. So here's what would happen. This would turn positive. This would not. Since the number you plug in has to be the same in both places, it's always going to cancel with itself. But you're going to end up with an answer of -1 because this will be positive This will be negative. And you're heading towards negative 1. Even though you're not allowed to plug in a 0 per se.
On number 17, like most problems, the best thing we could hope for would be to be able to plug the 6 directly in. Unfortunately, that's going to give us 0 over 0, because you'll have 4 minus 4 over 6 minus 6. And we've been factoring to solve these problems, but this is not a factorable situation here. So we have to dig back into Algebra 2 or Pre-Calc and come up with another way. And that way is to multiply by the conjugate. And more specifically, we want the conjugate of the numerator because, let's face it, it's a little nastier looking. So we're going to multiply by what amounts to a giant orange 1 in the form of a conjugate. Here it is. Now, at first it may look like we're taking a step backward, but this is not going to be as bad as it looks. In fact, it's going to work out pretty smoothly as we FOIL it out. Do a little double distributive. That's just going to be a regular x plus 10. It'll simply be the radicand. The middle two steps are going to cancel each other out. This will be positive 4 square root of x plus 10. This is negative 4 square root of x plus 10. I'm not going to write either one of those because they add up to 0 anyway. And finally, the last multiplication step is going to give us a negative 16 or a minus 16. All right, I'm going to copy down the denominator, but I will purposely not FOIL them, not because I'm lazy, but because I'm savvy. You'll see what I mean. Okay, there we go. And the reason I didn't bother to FOIL the bottom was because we have a pair of x minus 6's that are ready to be canceled. You can see that up in the numerator, this actually is an x minus 6. And that's going to cancel with this x minus 6 right here. They're both gone, leaving us with, again, a placeholder of 1 up top. Now, we can plug the 6 directly in. And that's simply going to be the square root of 16 down there, which is 4. So we have 1 over 4 plus 4. And so the limit, as x approaches 6, is 1/8. And again, we realize that if we were to graph this f of x equation, this would be a point discontinuity at the point 6 comma 1/8 because the limit does exist there. So that's number 17. For our last two examples, we're going to employ the squeeze theorem. Sometimes it's called the sandwich theorem. It basically has the same idea behind it. And that is that one function, in this case it's the blue function, is always sandwiched or squeezed in between the red and the green. So I went ahead and made f of x blue, just to kind of color code everything. And you can see that blue stays between red and green, or at least after a while it does. Perhaps in its early life, blue was a little reckless, but after a certain point in time, and moving forward to the right, blue decided to mature, I guess, and stay in between red and green. If that eventually happens for all x in an open interval, and there's a point called C, and that C has to be in this interval, so C has to be somewhere over in this region when blue is, in fact, between the other two. The squeeze theorem goes on to say, if the limit as x approaches C of h of x equals L, which in turn is equal to the limit as x approaches C of g of x, then the limit as x approaches C of f of x will exist and is equal to L. That seems pretty wordy, but it actually makes a lot of sense. Here, let's go with the color coding again. H is what I turned green. So it says right here, as I'm underlining, the green function, h of x, as x approaches C, let's say in this case C is infinity. We'll take it all the way out to the right. We are approaching a height of L, which you can tell is 0. We are approaching 0, getting closer and closer to the x-axis. And then let's say that g of x which I have colored red, that is also approaching L, which again is 0, as x approaches C, which is out to the right. I made that infinity. Well, as you head to the right, if red is heading towards 0, and green is heading towards 0, and blue has to stay between them, then blue has to also approach 0, because it's being squeezed or sandwiched between the other two colors. So the limit exists, and it's equal to the same thing. In my example, I made it 0, but it could really be any number. And the squeeze theorem is becoming a lot more prevalent on AP exams, and in particular, multiple choice style questions. Here's a couple examples that I took inspiration from College Board and made my own, number 18 and 19. Originally, I had said that there were going to be 20 examples. Well, that's not true. There's only 19, so you got a break. Here's number 18 with the squeeze theorem. Notice that I did not mention squeeze theorem by name. I want to see if you realize that's what's happening here. Number 18 goes on to say, let A and C be functions defined by, and then you can see their equations. A seems to be an upside-down parabola. C is linear. And B is between them. Okay, so I'll make B blue. It'll be between the other two all the time. And we want to know, hey, what's going on with B, which again is the blue function, as x heads towards 2? Okay, well, if B has to stay between them, let's make A red, and we'll make C green. Let's see what they're up to when they head towards 2. What if we took a 2 and we plugged it into the A function? What would that give us? Well, it would give us -4 plus 14 minus 3, which happens to be 10 minus 3. That's going to be 7. All right, equals 7. That's the A function at 2. And now what we'll do is we'll head over to the green function that I called C, and we'll figure out what's happening to C when we're at 2. Well, if I plug a 2 into the C function right here, I'm going to get 6 plus 1. That also happens to be 7. So when x is 2, A goes through the point 27, C goes through the point 27, and B is between A and C, as you can see right here with this inequality. And if they're both heading to a height of 7, B has no choice. B also has to hit 7, or the point 27, so the proper answer, the correct answer, is choice B. All right, let's try one more multiple choice problem based on squeeze theorem, and that would be number 19, and then we're going to call it quits. Again, same sort of deal. You've got B in the middle. B is between A and C. It can be equal to them once in a while, but it has to stay in between otherwise. I'm going to go ahead and color code the other two. I've been calling C green and A red, so we'll stick with that plan. All right, what's happening to B as we approach x equals 1? As x approaches 1, what is going on? All right, well, let's start with the red. Let's start with A of x. If we put a 1 in right here, we've got sine of pi over 2. Hopefully you're good at pre-calc, or at least the unit circle. Sine of pi over 2, or sine of 90 degrees, is going to be 1. Plus 2 is 3. So A goes through the point 1, 3. Okay, let's try the C. We're going to try C of 1. So if we put a 1 in here, then this is going to be 4 minus 3, which is 1. So C is going to go through the point 1, 1. B has to stay between them. So when B gets to 1, we know that we have to be between 1 and 3, a height of 1 and 3. But that doesn't mean we have to be at 2. I realize that 2 is halfway. But there are millions of numbers between 1 and 3. Think of all the fractions and decimals you could be at. And there just simply isn't enough information. A and C are not squeezed or sandwiched tightly enough for us to actually know what's happening to B. These numbers right here, the 3 and the 1, would have had to match each other for us to actually be able to pick an answer. So the correct choice is D. The limit just simply can't be determined from what we've been given. And that wraps up the lesson for today. Hope you enjoyed it. Take care, and we'll see you when we meet again. Bye-bye.